Recording in progress.
Yeah, can fun everyone. So last class we wrapped up with friction. We'll be starting off with circular motion. There. So circular motion is again, it's a combination of everything that you learned so far. So everything comes up: vectors, calculus, kinematics, NLM, friction, everything. So in that way, it is not that tough because everything is the same thing which you're saying. We're just adding one more ingredient now. So in case of friction, we found friction, then we kept it an FBD. In circular motion, we will see. So in this, there are three parts. The first thing is the circular kinematics. The second thing is uniform circular motion, and then we'll have non-uniform circular motion and radius of curvature. So yeah, it's an interesting chapter. So let's see. So first thing is the circular kinematics. So first thing we define something called angular position. Theta. So angular position is simply the angle made by the reference position vector with respect to the reference. Meaning, suppose if a particle is going in some weird path like this, if you choose this dotted line as your reference line, if this is your R bar, this would be your angular position. So with respect to that line, what is the angular position? Now be careful in this, we don't care about the magnitude of R bar. What we are interested is only the angle it makes. You can also take a circle. So first you have to define your reference line. With respect to what line are you measuring your angle? This is your R bar and this is your angle theta. So in this case, the magnitude of R bar is, we're not interested in that. It is simply the angle subtended. That is how we define what is, position. Position is simply XYZ coordinates, isn't it? For angular position, it is an angle with respect to what? A reference. For angular displacement, magnitude is not necessary. Magnitude of R bar is not needed. So this is the first thing, angular position. Clear? Next thing, angular displacement. Again, if you see, it kind of looks like kinematics only, the definitions. So angular displacement is delta theta, is theta final minus theta initial. So theta has an angle. It is a direction. So if you're rotating this way, it is clockwise. We use right-hand thumb rule. So this is minus k cap into the plane. We have done this in pseudo vector in vectors, if you remember. We will discuss that also in detail. Suppose if you're rotating this way anti-clockwise, The direction is plus k cap, we take out of the plane. So the direction, right, is given by your right hand thumb rule. So this is your rotation, and the thumb gives you the direction. This is a pseudo vector, meaning it is not the real direction. We have done this in detail. Vectors. Sure. Pseudo vector, page 62. We did this in detail, but I'll just brief it up again. But you can refer page 62 vectors. So in this case, so look at this thing. So if you're looking at my screen, right? So if you take your right hand, if my fingers are going this way, thumb is pointing up. So meaning this rotation, that is this rotation, which is anti-clockwise, is giving you finger into the plane, isn't it? It's coming out of the plane. If you rotate this way, the finger is pointing downward. So anything that is rotating this way, so we are saying it is rotating, it depends on how you're saying it, rotating clockwise, we say the direction is downward. So it is not the actual direction, it is a pseudo vector. So the thing is, when it goes in a circle, right, there'll be infinite directions. So it becomes very cumbersome to define. But let me define it more ways. So curl of the fingers gives you the rotation. Curl of the fingers gives the rotation. And thumb gives you the direction. Let me give an example. For example, let's say this is your reference. So if something rotates this way, theta 1, let's say this is pi by 3. So vectorially, you'll write like this. So theta 1 is pi by 3. This is rotating which way? Anti-clockwise. So this is k cap, isn't it? This is an anti-clockwise. So your fingers, you will make a fist, you will curl the fingers in the anti-clockwise direction. Thumb will be coming out of the plane. So this will be useful to figure out which way is the particle rotating. If something rotates like this, and let's say this theta 2 is pi by 4, then you will write theta 2 is pi by 4 minus k cap. That is clockwise. So minus k cap meaning put your thumb into the paper and rotate your fingers. That will give you the rotation. That is the clockwise direction. You're getting it? And be careful. Pi radians is 180 degrees. So we write everything in radians. So if someone tells you the fan rotates, 210 degrees k cap, that is the meaning of it. So let's see a brief a little about a pseudo vector again. So what is the pseudo vector which I keep talking about? This will keep coming here, pseudo vector. So be careful. This like can come in rotation. Wherever there is a rotation, all rotation quantities are pseudo vectors only. So pseudo vectors, it is the same thing which we discussed there. It gives us the sense of rotation and not the actual direction. That's why we call it pseudo false vector. So why do we need to define? Think about it. If a particle is going on a circle, when you're here, what is the direction? J cap. When you're here, what is the direction? Minus I cap. When you're here, what is the direction? Minus j cap. When you're here, what is the direction? I cap. Every instant you have a different direction. It becomes pretty cumbersome to define direction for this thing if you're going in a circle. Then people said, yeah, let's define something more simple for us to figure it out. So particle going in a circle or any curve actually has infinite directions. Circle, right? Its direction changes every instant. So for convenience, again, getting it, this is not a concept, this is more of a convenience. For convenience, we use right hand rule. Where the curl of the fingers is the rotation and thumb is the direction. Example, let's say this is X, this is Y, and this is Z. Suppose if a particle, right, is going like this. You're getting how it is going? This thing is a circle. This is X and this is Y. So this is a circle in YZ plane. Can you tell me what will be the direction? The particle is going in a YZ plane. Meaning if you're standing here and observing, क्या दिखेगा आपको? Think like this thing, na? See, the book is there. This is my YZ plane. Getting it? So this is my x-axis. If you're seeing, this is my x-axis. Clear? So how am I seeing the circle? It's going like this, right? You're getting it? It is going like this. So I'll take my right hand. I'll put like this. This is the rotation. So thumb is pointing which way? Towards me, na? So what is the direction for this circle?
Sir, but the circle is not actually moving forward, right?
Circle is not going forward.
But it's just a way to represent if it's going.
Yeah.
If
Bus clockwise anti-clockwise के लिए direction तब. Sir, no one is going in the direction of axis. Is this clear, everyone? So इस circle के लिए direction what will I say? So we will say example, it is doing 2 revolutions per second. We will say I cap. No one is actually going along I cap. Are you getting the meaning of this? So the meaning of this is the thumb is in the direction of I cap. So put your thumb along the direction of x-axis and the fingers will give you the direction of rotation. You getting the meaning of this? For example, if I give you one more example, if I say a particle is rotating 3 revolutions per second minus j cap, can you tell me how is it going? Put your thumb along minus y-axis and then rotate your fingers. That will give you the rotation ka direction. How is that? So this is x. I'll take this is y. This is z. So meaning you're saying the thumb is in this direction minus this thing. This is minus j cap. So put your thumb along minus j and rotate. So this guy is going in a circle like this. So particle is going in xz plane. And for a person who's standing here and observing this, उसको क्या लगेगा? It is going which way? Anti-clockwise, na? Is this making sense, everyone? So pseudo vector is mostly a convenience. You don't want to get into the headache of finding direction every instant. So if someone tells you the particle has a rotation of 10 revolutions per second I cap, he doesn't mean particle is going along x-axis. What he means is put your thumb along x-axis and the fingers will give you the rotation ka direction. Is this making sense, everyone? We have done more examples in the vector, pseudo vector. Same thing we did there also. But I thought I'll just brief it up one more time. Let me give you one more example. Maybe this would be better. Suppose this is x, this is y, this is z. What if circle is going like this? Now what? So it is going inside, right? So thumb will point this way, na? K cap, isn't it? What if this guy is going like this? Now, what is the direction for this guy? This way, right? Minus j cap. You get in the directions? So it doesn't matter. You can have any weird circle also. What if something is going like this? Then what will you take? Again, it depends on how you're going here. It can be this direction. Getting? So it is going in here, it is coming out from here. Able to visualize the direction? So you have to rotate in that way. So the vector will point in some direction. Is this clear, everyone? So pseudo vector, be careful with that. So in rotation, whenever you talk about I cap, j cap, k cap, no one is actually going in that directions. They're indirectly giving you the thumb ka direction. Clear? And to get the rotation, you have to use the right hand thumb rule. So that is one. Next thing, when you talk about angular displacement, now be careful. If particle completes one revolution, displacement is zero. So let's call it linear displacement, because now you'll unnecessarily get confused between displacements. Till now, what we said was linear displacement was zero. But if we ask you angular displacement, it is 2 pi. Because angular displacement, right, it is depends on which way you're rotating. If you want zero angular displacement, you have to rotate it backward. For zero angular displacement, it should be like this. If you're rotating one in this direction, then you have to rotate the other one in that direction. So this is this way and this is this way. So this will be plus 2 pi, this will be minus 2 pi. Then we say it is zero. But if you just make one revolution, we will say it is 2 pi. If you make one revolution forward and one revolution backward, then we get zero. Clear? And this thing, I taught you also, if you remember, using a, where is this? I don't have a water bottle close by. I don't have a water bottle here. Think of like this. If you look at a right hand screw, right, for example, say this bottle is there. I want to open the cap. You want the cap to come outside. So what should you do? This is the rotation. So if I rotate this way, the cap is going to come out. You want the cap to go inside, put your thumb down and rotate. Rotate this way, the cap goes inside. So these are all right hand screws. You can check out with your water bottle. Same thing happens. कभी हुआ when you want to open a screw or something, कभी कभी confusion होता है. Should I rotate this way or rotate this way? So right hand works. Getting it? So all your in the house, right? If you see your taps, your screws, anything, right? Most of them are made for right-handers. So right hand screw rule. So if you want something to go in that direction, it works that way. If you have your Camlin, na, whiteboard marker, that's a left hand screw. It doesn't work for that. Camlin वो white marker है ना, because you don't want to open that cap frequently, right? So the screw is reverse. It's a left-handed screw. If you actually use right-hand rule, it becomes tight. So your water bottles are right-hand screws. Your Camlin whiteboard marker is a left-hand screw. These people are opening caps now. Try. Clear? So it has its own uses in case anytime you forgot how to rotate a screw, it works. The next thing, clear with angular displacement? Next thing, angular velocity. The symbol is omega bar. We call it omega. This is nothing but rate of change of angular displacement. It kind of looks like kinematics only. There it is position, here angular position, velocity, angular velocity. Rate of change of angular position. So omega bar is nothing but d theta by dt. So omega bar is also pseudo vector. So if you want to find omega average, that is simply theta final minus theta initial by time. So angular displacement will be integral omega dt. This is nothing but area under omega t graph. We will not get into all this. It's the same as kinematics, what you have done. That means if you have a graph with omega t, and if you have a graph with theta and time, so area below the time axis is negative area. Area above this thing is a positive area. So that area will give you the change in angular displacement. Similarly here in a theta t time graph, if you look at the slope, so in a theta time graph, slope d theta by dt will give you omega. There, have a look at this. Clear, everyone? Next thing. To consider a particle going in a circle, if this is theta, this would be your arc length s is equal to r theta, and this radius is r. And this particle here is going in a circle, we'll call it v tangential. It is just going along the tangent. So we know the arc length is equal to r theta if you differentiate with respect to time. We get ds by dt is equal to r into d theta by dt. Since s is the arc length, ds by dt will be the tangential speed, which we call it as v tangential, which is nothing but r omega. The vector form can be written as v tangential. Be careful, this is not the full velocity, it's only the tangential velocity. Is given by omega bar cross r bar. This is the relation between the linear speed and angular speed. Have a look at this.
So what is the difference between the capital R and small r?
R bar is just a vector.
It's also same thing.
Same thing, just vector था वो. R is that radius, na? We'll do one thing. If you're confused, let me make everything smaller only. ठीक है? Same thing. It's a cross product god vector. Dot product में vector कहाँ से आएगा तुझे? This is a cross product, not a multiplication. Because omega is a vector, R bar is a vector, V bar is a vector. If you use omega dot R bar, you won't get a vector quantity. Clear? And if you look at this is R bar, this is V bar, omega bar is out of the plane, isn't it? Omega cross R should give you V bar. Let's see a question. We have a particle here, 0, comma d. This particle is going in a straight line with speed v. We have an observer standing at the origin and observing the particle. A particle moves parallel to x-axis at a height d. Find the angular position and angular displacement and angular velocity at time t as seen by the observer at the origin. Now, the biggest mistake, everyone thinks, but ये तो circle में नहीं जा रहे हैं ना. Again, understand one thing. How did you define angular displacement? The angle made by the position vector. Now you tell me, after some time, what will happen? Initially, this is your R bar, agreed. Next moment, this is your R bar. Next moment, this is your R bar. This is your R bar. This is your R bar. Isn't this angle changing? That's what I said. I don't care about the magnitude of the vector. What I'm interested in is how fast is that vector rotating. So the most common mistake, na, just because it is circular motion, सबको लगेगा particle circle में जाना है. You can even define angular velocity for particles going in a straight line. You're getting it? So the definition of angular velocity or angular position is the rate of change of angle. It has nothing to do with circle. Circle is a very special case. That's the reason in the beginning I defined like this. Theta is simply the rate of change of angle with respect to the reference. So after some time, it will go like this. So this is theta. So I'm asking you that what is this theta at time t and what is d theta by dt at time t, the angular velocity. Take a minute, give it a try. Then I'll show you. Let's see. There are two ways to do this. One, let's do completely mathematically, and one, then let's use the actual definition, like what it means in the first place. So after some time t, you will be somewhere here. You're going like this. This is your r bar. So the angular displacement you're talking about is this angle. This length will be v into t, and this length is d. It is just a right angle triangle. So we can simply say tan theta is equal to vt by d. And you can simply say angular displacement is tan inverse vt by d. That will do. That's it. There's nothing more to do there. Next, what do you want to find? You want to find the angular displacement. Now, how do we do that? So we have tan theta is vt by d, differentiate with respect to time. Tan ka differential will be secant square theta, but remember you're differentiating with respect to time, so this will be d theta by dt, chain rule. And this will be v by d, dt by dt, which becomes 1. So from here we get d theta by dt, that is the rate of change of angle, is v by d sec square theta. D theta by dt is nothing but omega. That's your angular velocity. So this is v by d cos square theta. But what is cos theta? I already know tan theta. If I know tan theta is vt, this is d, this is the hypotenuse, root over d square plus v square t square. You can find cos theta from there. V by d cos theta will be d by hypotenuse, root over d square plus v square t square ka square. 1d will cancel, you end up with vd by d square plus v square t square. This is your omega as function of time t. Check. Your final answer should look in terms of v and d and t. That's it. Those are the only three variables you know. Please check your calculations. This is pure maths. There's another way to do this. First, have a look at this. So someone asks you angular velocity, they're literally telling you find angle as function of time t and differentiate. Is this clear, everyone? Alternate. There's another way to do this. Because sometimes what I taught you right now will become very complex. Listen carefully. And you know this method. We have done this. After some time, you'll reach somewhere here. This will have a velocity v. This is your angle theta. So this angle would be 90 minus theta. If you look at the components, this would be v cos 90 minus theta, v sine theta. This would be v cos theta. This v cos theta is your tangential speed, isn't it? What do you mean by tangential speed? Perpendicular to r bar. This is your tangential speed. And what is v sine theta? This is called radial speed. Anything in the direction of radius is called radial speed. And this distance is d. And this distance is r. Just now we defined what is omega. Omega is nothing but v tangential by r, isn't it? What is v tangential? V cos theta. Now, why are you saying that is v tangential? Think about it logically. V sine theta and v cos theta, who is responsible for changing the angle? If the particle goes this way, can angle theta change? So v sine theta is not responsible for changing the angle. V cos theta is responsible for changing the angle. And what is r? R is nothing but from here, cos theta is d by r. So r is d by cos theta. Check. Same answer we got. V by d cos square theta. Substitute cos theta का value. We get v by d cos square theta would be d square by that thing vt. This is d square plus v square t square. This is much faster. Integration कुछ नहीं है. Same answer. Anyone remembers what is v sin theta? D by dt mod r bar. Remember rate of change of length of the vector. You know where we have done this? Kinematics. We did this little extensively. We studied this. Do you guys remember this question now? Radial velocity. And that day when we did this question, we ignored u sin theta. And I said we will see that later on. That u sin theta is your tangential speed. dr by dt is called radial velocity. U sin theta is responsible for rotating the vector. So that's why that became v tangential. If you're remembering something like this, you should definitely go and refer to this question. We did this pretty detailed. This is page 35, kinematics. This is how you'll be learning. You'll be keeping going front, back, we'll keep jumping. So in kinematics, we ignore that v cos theta in this case. So clear, everyone? So there are two ways you can do. Both are right. Which one was convenient? Let's see one more. Let's see one more. Particle is projected with u and theta. Gravity is there. This goes up, comes down. This is your origin. Find omega of the particle. As seen by the origin. This is important. Observer is important. If you don't define the observer, omega I can't define. Because that r bar ka vector has to start from somewhere. As seen by the origin when the particle is at h max. There, your projectile motion. I know you're missing it. You're not missing it. Let's get this. What do you guys think? If you try to use differentiation, you will go mad. Use that alternate method. See. So first thing, you want to study at Hmax. So at Hmax, what is the velocity? I hope you remember. U cos theta. So from here, you're looking at this guy. Getting it? So you're interested in this angle actually, isn't it? That is the rate of change of angle. Now you tell me, this component is there. This is u cos theta ka cos alpha. This component is u sin theta ka sin alpha. Sorry, u cos theta ka sin alpha. And this dark line, this black line is your r bar. Who is the tangential velocity here? This is your v tangential, isn't it? That is responsible for changing your angle. Basically, the one which is perpendicular to r bar. So what is omega? Omega is simply v tangential by r. In this case, it is u cos theta sin alpha by r. Now, how to find that? Now, this height is how much? H max. How much is this? R by 2. So from here to here, this is your r bar. This angle is alpha. So r is nothing but root over h square plus r square by 4, where r is the range and h is the maximum height. And what is tan alpha? H by r by 2. It's pretty messy actually. So we will leave it here. We'll not try to substitute. If numbers are given, you would have got something good. There, right? You know everything. You know r, you know alpha. If numbers are given, you would have got something. So using that second method, right? Using that v tangential, you'll get answer pretty fast. Is this making sense, everyone? So simply at every point you take the velocity, draw your r bar, and resolve the velocity along r bar and perpendicular to r bar. So this u cos theta cos alpha is responsible for stretching the vector. U cos theta sin alpha is responsible for rotating the vector. So you take the v tangential by the distance will give you omega. That was the whole theme every time. Is this clear, everyone? The reason why I gave you these two questions is, first thing, don't think circular motion matlab questions will come only in circular motion. That omega is not only defined for a circle, omega can be defined for any kind of path. Clear? That is the first thing that should go into the head. Because the most general common misconception is people think only circular motion may you'll have omega and all. Not necessary. You can create omega for anything depending on where you're seeing. Is this clear, everyone? Daksha.
So I tried differentiating. So I got
हाँ.
the relation tan equal to tan theta by 4. So after that I got d alpha by
जिसको
4.
ये लेके इसको डिफरेंशिएट करना पड़ेगा.
Yes, sir.
हाँ, then you will get it, but it will be very complex. Same आएगा.
So but I got two unknown things. I got d alpha by dt also and d theta by dt.
नहीं भाई है ना, अरे थीटा कांस्टेंट है ना रिकॉर्ड.
Okay, sir.
थीटा इज द एंगल ऑफ प्रोजेक्शन, वो तो दिया है ना, वो तो जीरो है. डी अल्फा बाय dt is omega. Clear?
Okay, sir.
Let's see one more. Let's see something a little more simple. particle is going in a circle with speed u. So the particle is somewhere here, which is going with speed u. Radius is r. This is O. This is A. O is the center. This is a standard question. This came in the exam before. This is a point on circumference. Find omega of this particle as seen by O and as seen by A. So the same particle can have different omega depending on who is seeing it. Seen by O and A. Why? Think about it. Listen. When you ask O to look at it, what angle will you look at? He will look at this angle, isn't it? If you ask A to look at, what angle will he look at? He will look at this angle, right? Both angles are different. They're looking at two different angles ka rotation. So for the same particle, depending on where you're watching, you can have different omegas. So before going into the standard ones, I wanted to show you the weird ones because it should get drilled into the head. Omega can be defined for anything. Omega can be different from different positions. Because the most general misconception सबको वही लगेगा. Omega is defined for circle and हर बार center से ही देखना है. Not true. You can stand anywhere and watch. Give it a try. Right, Vihan. Let's see. Now, first, if you ask O to C, O ka life is easy. This is your R. This is perpendicular, so straightforward. So O will say V tangential by R, V tangential is U, and radius is R. Done. But problem for A is when you try to draw that line, that angle is not 90, isn't it? So we need to divide this U into components along the line, perpendicular to line. You can do it. I answer eventually. Little headache, but there's a better way to do this. If this angle is theta, this angle is theta by 2. Do you agree? In tenth standard geometry, there's a theorem based on this. But still, if you don't know the theorem, chalega. If that is theta, this will be 180 minus theta, right? If that is theta by 2, this has to be theta by 2 because it's an isosceles triangle. Fair enough. Now, if you go back to omega of O, so omega of O is nothing but d theta by dt, which is u by r. So if you ask omega of A will say, okay, my angular velocity is d by dt of theta by 2, which is half of d theta by dt, which is u by 2r. That's it. That means the same particle, when A and O are looking at it, A thinks the particle is rotating slower, isn't it? The angle subtended is always half of angle subtended at O. So O will think it is going with u by r, A will think it is going with u by 2r. So angular velocity as seen by A is smaller compared to angular velocity as seen by O. Is this making sense? So depending on where you're standing and watching, your omega can be different. And this is something which you notice every time. Maybe you didn't realize. Ever notice this when you're sitting in a car or a train and you look outside? The road feels like it's going very fast. Now tell me one thing. Listen, when you're in a car or something, now if you're going with velocity v, okay, and let's say there is a tree here and there is a tree here, by relative velocity, you will think both the trees are going back with the same speed. Agreed? Then, but why do you think this tree A is going faster than B? Again, listen, when you're going in a train with 50 kilometers per hour, the road below you and the tree ahead of you both are going with 50 backward. Then why do you think the road is going faster than the tree? What do you guys think? The thing is, the problem, this is more of a biology thing. What you're looking at is not velocity. We humans cannot see velocities. We humans are angular creatures. What we see are always angles. Think about it. You have your finger. Which is bigger, your finger or me? Obvious, right? I am the bigger one. Put your finger in front of the eye. Now, who is bigger? The finger is bigger than the table in front of you, isn't it? If you have a building in front of you or a book in front of you, ask yourself, see, if I take a book and if I take a finger, right? If I put the finger in front of it, my finger will be bigger than the book. Isn't it? This will go over the book, see. Your finger ka thing will be bigger than that. What is the reason there? The thing is, you are actually not looking at lengths. Suppose if I have a tree here of 10 meter and you're standing here and observing this, let's say from a distance of 1000 meters. And let's say we have a tree of 30 meters, but you're looking this from a distance of, let's say 100 meters. And let's say you're looking this at a distance of 1000 meters. So this person will think this angle subtended theta is 1 by 10. This person will think this angle subtended theta is 30 by 1000. That is, how much is this? 3 by 100, isn't it? So you will think this 30 meter ka tree is smaller compared to the 10 meter ka tree, isn't it? So then now you tell me, are you actually looking at lengths? We humans are never looking at length. You don't know what is length. Our eyes cannot see length. What you're looking is angles. Try to observe this. Now see, you can see this black thing which I'm showing on the screen. Now just try to observe this. Don't turn your head. Just look at it with your eyes. So when I'm rotating this, what are you looking at exactly? Can you notice what you're saying? The line joining your eyes to that black thing, that line is rotating, isn't it? Now, same thing again. Now try to look at this. What is happening now? The angle is changing much faster. So what you're looking at is not velocities. You're not looking at lengths. What you're looking is angles and angular velocities. So in that thing which I told you, when you're going in a train, the tree which is closer and the tree which is farther, both have same speed v, but this distance r1 and this distance r2 is less. So this guy ka angular velocity will be v by r1. This angular velocity is v by r2. So in the given amount of time, it will give you an illusion this thing has rotated more angle than that angle, isn't it? So you will feel the road is going faster than the tree. Are you getting it? So when you're going in a car and when you look at the road below, it feels it is going faster compared to a tree which is a little far, is because the angle is rotating much faster. You are never looking at lengths. Your eyes cannot, your eyes don't know what are lengths and your eye don't know what is velocity. Human eyes measure angles and angular velocities. Make sense? Did you ever observe this thing? When you're, riding your cycle, when you look at the cycle ka wheel, sometimes you'll find the wheel is going front and the wheel is going back. Anyone noticed it? Currently, anyone ka fan is rotating. Wait, I'll do one thing. Anyone ka fan is rotating? Can you just point their screen towards the fan? Ansh, तेरा fan clarity नहीं है रे. Can we have any other better fan? दिख रहा है actually. If you can switch on the light, I think we can see. Ansh, light on कर लो एक बार and show her the fan. I'll show you right now what I'm saying. Now look at Anshka fan. Can you see? नहीं इतना clear नहीं है रे. Wait, I think I have to switch on my fan only. I'm not sure. Oh, this also will be. Let's see. There, Devansh ka fan दिख. Look at Devansh ka fan in the screen. Did you observe something? Can you see how the fan is looking? It's rotating. It's looking like it's going front to back, front to back. दिख रहा है? You never noticed that? You would have noticed this on your cycle also. When you're riding your cycle, you can see the front wheel, right? It is going front and back. That fan is looking like an illusion, right? It's looking like someone is switching it and switching it off. So why is that happening actually? Again, same thing. We humans, right, have something called persistence of vision. Ever seen this thing? 24 frame rates. So what we can see is 16 frames per second. So when you're looking at a video, you must have done this thing, na, 60 FPS or 144 FPS frames per second. That's what it is. If you put 16 photographs in a second, you think it's a video. Eyes cannot distinguish between two photos with a gap of 1/16 second. Ever played with that flip book? You flip that book and it gives you an illusion someone is hitting like this. So that is what actually do in a theater. If you look at a movie, right? When you're looking at a video, what you're doing is simply you're taking photographs and you're playing them so fast, your eye thinks it's wheels of a car also. So that gives you an illusion. You're looking at a video. Now see, this is what happens with your eyes. Imagine we have a rod. Now the reason why the fan is looking so weird is because of this. Rod is there. Let's say it is rotating. Now your eye, right? Your eye is like a camera which is taking photographs every 1/16th of a second. You're getting it? Your eye can't see video. Your eye is actually taking photographs, and the photographs is your brain is processing as a video. Now, in 1/16th of a second, imagine when your eye takes a photo, next photo, the rod is here. Now, you tell me, what will your brain think? Your brain always perceives the shortest distance. Your brain will think the rod has gone from here to here. Agreed? Let's say rod is a little faster. Let's say the rod has come here. Now, what will your brain think? The rod has gone from here to here. Agreed? Let's say rod is even faster. Now, what will your brain think? The rod has gone this way. Even though in reality, the rod is actually going like this, your brain will perceive the rod has gone in that direction. So your brain will think the rod is rotating in the opposite direction. If I increase the speed again, then what will happen? Your brain will think it is rotated this way. Now, if I can increase the speed such that the rod comes back to the same position, then what will happen? You will think rod is not moving. You can actually do this with your phone. There's a particular app or something, you can change the frame rate. If you can make the frame rate equal to the fan ka rotation speed, and if you put the video, it looks like fan is at rest. So how does that look? It looks like this. That's an helicopter. So what this did, the camera guy, he made the frame rate of the camera equal to the rotation of that helicopter ka wings. So every time it is taking a photograph, the wings are at the same place. So it gives you an illusion the wings rotate nahi ho raha hai. But you can see niche na ships and water, everything is moving. Looks like magic. Actually, those blades are rotating pretty fast. It just feels like they're not rotating. That is how it looks. Clear? So there, your whole life is a lie. You have never seen a video before. You have never seen velocity. You have never seen length. Your entire eye structure is based on angles. This whole chapter is about that. Your entire life is based on angles, and unfortunately, we think we are looking at velocities and lengths. Clear?
So, but when we normally see the fan, we don't see that illusion clearly, right? Like
You
when we
don't.
see
No, you see
camera,
that. Keep the chain ka fan ka speed. You sit and you try to observe. दिखेगा fan reverse में जा रहा है. You didn't notice it enough. Put the fan on full speed, or put it on speed 3, 4, then see, and then increase the speed and see. If you just clearly observe, ना तुझे clearly दिखेगा fan ऐसा जा रहा है and suddenly it goes reverse. Never observe that. Camera में you can see more clearly because you know why? This Zoom ka video call, right? It has a variable frame rate. So it is recording at a different levels of frame rate. So you can clearly it's more visible on this thing. Try to observe that today, right? You just switch on the fan, just sit there and watch, observe. See it from the bottom, huh? Sleep and look at the fan. दिखेगा. Clear? So now you know
yes,
when you're going in a train or a bus, why the road feels like it is going faster compared to a tree or a mountain which is very far. The same reason when you look at your cycle ka wheel also, na, it car ka tires also, it feels like the tire is going front and then back. So all this happened because of that persistence of vision. You're looking at angles and angular velocities. Clear, everyone? Next thing. So we have a wall here. We have a laser. So this laser ka light, right, is falling on the wall. This is the P. So P is the laser ka spot. You must have done this with your cat or dog to tease it. And let's say this distance is 100 meters. And this laser here is rotating at an angle of omega 0.1 radian per second. So this angle is theta. You're getting how it is? I'm pointing the laser and I'm rotating like this. So the laser ka spot will move on the wall, no? So initially laser ka spot is here, then it is here, then it is here, then it is here. So spot is continuously moving on the wall. Find the speed of the point P when theta is 60 degrees. Find speed and acceleration of point P. When theta is 60 degrees. So with what speed and what acceleration is that spot on the wall traveling when theta is 60 degrees? Let's get this, everyone. Let's just find the speed. Acceleration is the same thing, just double differentiation. Let's find speed. Acceleration is the same thing, just do double differential. Give it a try. Just give it a try. I'll get some water and come. How do we do this? 40 meters per second. Okay. Let's see. This is the standard one. So when the point P goes, what changes is this coordinate, isn't it? What is changing is the height of the point P. So that means rate of change of point P. So velocity of point P nothing but dy by dt. Agreed? Isn't it? When the point P goes upward, what changes? Only the y coordinate changes. So rate of change of y coordinate must be the speed of point P. And what is y coordinate? We know tan theta is y by 100. So we get y is equal to 100 tan theta. Differentiated. So dy by dt is 100. Tan ka differential is secant square theta d theta by dt. This would be velocity of point P. This is 100 and angle theta is given 60 degrees. Remember, you have to put 60 after differentiating, not before. This would be cos square 60, so that is 4, and this guy is 0.1. 40 meters per second. Check. Is this clear, everyone?
Sir, can we use the formula V is equal to omega R in this?
V is equal to omega R. Now, what is V and what is omega here? Which V will you take? Is V the full speed?
Okay, sir. It is a component.
ना VP ना तो VP का component लेना है और ये लेना है. So तुझे VP नहीं आएगा, VP का component आएगा, तो उससे वापस VP निकालना पड़ेगा. You'll get it. You can do that. ठीक है? All clear with this? Next thing. Now, how do you find angular velocity of one particle with respect to another? This is another important concept. So let's say we have a particle going with u1, theta 1. This is going u2, theta 2. This is A, this is B, and this is D. So if I ask you, find the angular velocity of B as seen by A. So first let's stop A. If I stop A, what A will think, okay, I came to rest. This point B is going with velocity u2 sine theta 2 minus u1 sine theta 1. And this side ka velocity is u2 cos theta 2 plus u2 cos u1 cos theta 1. You guys remember this? We did this in relative velocity. This is B ka velocity. So this is what A will think about B. This is the relative velocity of B as seen by A. Now you tell me, in this, what is the tangential velocity? This is your V tangential, isn't it? So this is how we define. So omega of B as seen by A will be u2 sine theta 2, u1 sine theta 1 by D. So this is your general formula, everyone. So omega is given by relative velocity perpendicular to the line joining the points. You take any 2 points, take the relative velocity perpendicular to the line joining the points by distance between them. Quite a useful one. So whenever you want to find angular velocity of a system, you can take any 2 points on the body, resolve them into components, take the perpendicular components. Yeah, this is for that instant. At that instant. If the relative velocity is changing, omega also will change, no? If you look at this question, after some time, isn't this continuously keep on changing here? This thing will go like this, isn't it? So distance to change ho raha hai na? So the perpendicular, this component also will keep changing. This is at that instant. Clear, everyone? So that's the basic idea. You stop one guy, and you will see 2 velocities. One is coming towards me, one is rotating. So obviously this guy is a V tangential. This distance is D. So I can ask questions like this also, projectile. What is the angular velocity of one projectile as seen by another projectile at so and so time? So the thing is, we always used to ignore this tangential component in kinematics, if you remember. That was always responsible for rotation. We never cared about it. Now it comes. Yeah, let's see a question. Let's see a question. So we have a rod here. Theta. Length L. This point A is going with speed U. So A is pulled with a constant speed U. This is point B. Find omega of the rod at this instant. Now, is the rod rotating? Think about it. If I draw the rod ka diagram, initially the rod was like this. Next moment, the rod is like this. Didn't the rod rotate? Didn't this angle change? Angle is changing, matlab there is an omega. Discussion closed. That's what I'm saying. Don't think rotation matlab only circle. You can create rotation for anything. As long as the angle changes, it's a rotation. So the theta 1 angle became theta 2. So it gives an illusion the rod is rotating. Find omega of the rod at angle theta. You guys should definitely do these questions, huh? They're not tough, but they're a little weird. Like whatever we have done so far, it's little completely different. नहीं रे बोरोजा, you got वो साइन नीचे आएगा. There are two ways to do. The first thing, let this distance be x. We can clearly see cos theta is equal to x by L. Differentiate. Just understand one thing. The moment I said omega, I want d theta by dt. So you need to differentiate. That is the idea there. So cos ka differential is sine theta, d theta by dt is equal to 1 by L dx by dt. Now, so what is dx by dt? Velocity of A, isn't it? When A is moving, x is changing. Agreed? So here we get minus d theta by dt is equal to, that will be u by L sine theta. We are getting minus n because the theta is decreasing. So omega is nothing but u by L sine theta. Easy? So at this instant, this is your angular velocity. How are you getting u sine theta in the numerator, right?
Sir, I use the other method.
Other method में देखते हैं. I'll show you that also. See, I mean the alternate method. The rod is going like this. This is VA. This is VB. Do you remember rigid body constraint? This is theta. This is theta. This is 90 minus theta. So this component will be VB sine theta. And this will be VB cos theta. I think you didn't take VB ka velocity. This would be VB sine theta. And this is VA cos theta. Now, if you guys remember from rigid body constraint, velocity along the rod must be same, or else the rod will stretch or compress. This you have done in NLM constraints. From the rigid body constraint, velocity along the rod VA cos theta must be equal to VB sine theta. Therefore, from there we get VB is equal to U cot theta. Now, from that formula, omega, we should take V relative perpendicular to the rod by distance between them. So V perpendicular is VB sine theta and VB cos theta. These two are perpendicular. This is VA. So the relative velocity will be VA sine theta minus, because minus VB cos theta, it's going in the opposite direction, by L. Take VB and substitute here. You end up with U sin theta plus U cot theta. That would be U cos square theta by sin theta by L. That will become sin square theta by cos square theta, U by L sin theta. Same answer. You have to stop B now, or you have to stop A, right? So relative velocity lena tha. You can't take direct A velocity. In this case, this method actually goes longer. So that method is pretty useful, when you're dealing with projectiles, especially. Something is flying and you're looking from somewhere else, this method is pretty good. But if you can somehow find angle in terms of x and differentiate, this always gives you the answer faster. Is this clear, everyone? Clear with both the methods? I hope by now it is drilled into their head. Omega is not only defined for circle. That is the main thing. Try this as a homework question. We'll discuss this in the next class. And I'm sure you remember this. We have an equilateral triangle. Side A. We have three particles. A is going with U. We have B going with U. We have C going with U. They are chasing each other. A, B, C chase each other with speed U. O is the centroid. This is how they will go. You guys remember this? We did a pretty detailed analysis on this in kinematics, in relative motion. This is the thing. This is how the particles will go, isn't it? When they're chasing each other, the triangle is rotating and shrinking. Should definitely refer to this. Solution is here only. Page 28 in kinematics. I hope all have the PDFs, right? Class notes ka I recently posted in the group also. Download them and keep it. Getting it? So now what is happening? If you look at this triangle is continuously rotating. So if you look at O and if you look at A, this is what you'll observe. This line OA, this is how it goes. This is the trajectory of A as seen from O. This is what the centroid thinks. That means at every instant, the particle is rotating with theta. Agreed? Next moment it will come somewhere here. Next moment it will come somewhere here. So the angle is continuously rotating. Find theta as function of time t. Find angle rotated by the vector OA bar as function of time t. Are you getting what I'm asking? It feels as if that O is going round, 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 round. So find the angle. How much angle will it rotate in time t? Is the question clear, everyone? This is what makes this advanced question. We have done this in relative motion there. Try this and come. Next class when we meet, we're going to discuss this first thing in the class. So next class when we catch up, we'll do a few more problems on this. We'll finish with the circular kinematics and we'll start with the introduction of uniform circular motion. So whatever I taught you today are actually little weird ones. These are all unorthodox problems. These are not standard models. But quite important. You will see the standard models in the next class. So we did almost 5-6 questions. So have a look at this, try this, and I hope friction you're doing, finish it off. Okay, with that we'll wrap up for the day. We will discuss the paper also if you have any doubts and any doubts in the class notes. If you have no doubts, you're free to